Somewhere beyond Neptune, Oumuamua still moves through darkness. Carrying answers, humanity may never recover from its brief visit here again. It crossed our solar system once, appeared late, and disappeared before scientists could determine what kind of object it was. Astronomers named it Oumuamua, meaning a distant messenger arriving first, yet its message remains almost completely unread by humanity today. Everyone agrees it came from another star system, but nearly every deeper conclusion still divides researchers across modern planetary science. That uncertainty transformed one faint point of light into the most controversial interstellar mystery ever recorded inside our cosmic neighborhood. Was Oumuamua a comet without a visible tail, an asteroid, or something belonging to no familiar astronomical category at all? Could it have been frozen nitrogen blasted from an alien Pluto, then reshaped during a journey between stars over ages? Might cosmic radiation have altered ordinary ice until sunlight released invisible gas, producing acceleration without any obvious cloud or tail? Or was it so thin and porous that radiation pressure pushed it outward, making a natural object appear deliberately engineered? Every proposal explains selected measurements, but every proposal also creates another difficulty that prevents a decisive conclusion from surviving scrutiny. The story began on October 19, 2017, when Robert Warwick examined images collected by the Pan-STARRS telescope in Hawaii. He noticed one faint point shifting between exposures, initially resembling countless smaller bodies already tracked throughout our solar system regularly. When astronomers calculated its orbit, however, the path appeared hyperbolic, proving the Sun could never capture this unusually fast visitor. The object had entered from interstellar space, becoming the first confirmed body observed arriving from beyond our planetary system directly. A theoretical population suddenly became real, and astronomers realized the galaxy was delivering fragments from distant worlds into our neighborhood. Planet formation is violent because young worlds collide, giant planets scatter debris, and passing stars disturb objects around systems constantly. Those processes should eject numbers of icy and rocky bodies, leaving them wandering between stars for countless millions of years. Before Oumuamua, scientists expected such travelers existed, yet nobody had ever confirmed one crossing our system through direct astronomical observation. Its discovery proved the darkness between stars contains debris, not merely isolated suns separated by vast and empty distances everywhere. For astronomy, that single realization changed our cosmic neighborhood from a closed system into part of a constantly exchanging galaxy. Unfortunately, astronomers found Oumuamua only after it had passed closest to the Sun and started racing outward toward darkness again. It had swept inside Mercury orbit during September, but nobody recognized the visitor, while the best observing opportunities still existed. Every passing night made the target fainter, measurements harder, and the possibility of resolving its surface increasingly impossible for telescopes. No spacecraft could launch quickly enough, and even powerful observatories saw merely a moving point rather than a detailed world. Everything claimed about shape, composition, rotation, and structure therefore came from indirect clues gathered while the object escaped observation forever. Its speed confirmed the interstellar origin, because the trajectory remained too energetic for the Sun to bind into returning orbit. Gravity explained most of the motion, accelerating Oumuamua inward before bending its path and sending it toward interstellar space again. A body ejected from another planetary system could follow exactly such a hyperbolic course, without violating any law of physics. Yet, after researchers examined smaller deviations, reflected light, and changing brightness, the ordinary traveler became increasingly difficult to classify confidently. The puzzle emerged not from impossible observation, but from several strange details refusing to fit comfortably within one natural explanation. The first surprise appeared in its brightness, which rose and fell dramatically as sunlight reflected from the tumbling object repeatedly. Such extreme variations suggested either an unusually stretched body, a flattened shape, or enormous contrasts across regions of its surface. Early artistic impressions showed a cigar-shaped rock, perhaps many times longer than wide, drifting through space like a needle. Later, analyses indicated a thin pancake might also match the limited measurements, changing the popular picture without resolving the uncertainty. Nobody ever photographed its outline directly, meaning every familiar image remains a reconstruction shaped by assumptions rather than visible detail. Brightness measurements also showed Oumuamua was tumbling, not rotating smoothly around one stable axis like many familiar asteroids in space. Instead, it appeared to roll and pitch through a complicated motion that could persist for an extremely long interstellar journey. A collision, close gravitational encounter, or uneven release of gas might have created that unstable rotation before discovery by astronomers. Without atmosphere, liquid, or strong internal friction, a small, rigid body has little ability to damp such complicated movement afterward. The tumbling was unusual but natural, demonstrating how one strange clue could attract attention without proving anything extraordinary by itself. Its surface appeared reddish, resembling irradiated objects from the outer solar system that have endured prolonged exposure to cosmic radiation. Radiation can darken carbon-rich material and create a weathered crust, offering evidence for an ancient journey through interstellar space. However, color could not reveal whether the interior contained rock, metal, water ice, nitrogen ice, or some unfamiliar mixture beneath. The object was already too faint for detailed spectroscopy, capable of identifying a decisive chemical fingerprint from its reflected light. Astronomers therefore knew its surface had been altered, yet they could not determine what material that altered surface protected underneath. At first, researchers called Oumuamua a comet, because objects arriving from distant reservoirs commonly contain volatile ice beneath their surfaces. Comets normally warm near the sun, releasing gas and dust that create a glowing coma and sometimes a visible tail, yet Oumuamua showed no obvious coma, no strong dust cloud, and no familiar gas emissions during the limited observing period. Because of this silence, astronomers briefly treated it as an asteroid, expecting its motion to follow gravity without additional forces. Then, precise tracking revealed the small acceleration that transformed an unusual discovery into an argument still unresolved many years later. As Oumuamua moved outward, gravity alone failed to predict its position, revealing a measurable non-gravitational acceleration away from sunlight. The effect was small, but careful analysis showed it was statistically significant rather than a simple error within the observations. Comets often receive similar pushes when sunlight heats ice, causing escaping gas to behave like weak rocket exhaust from nuclei. That mechanism could explain the motion naturally, yet telescopes saw none of the dust or gas normally accompanying such activity. Scientists had detected the push, but the engine producing that push remained invisible, creating the central contradiction behind the mystery. If Oumuamua was comet, why did it lack a tail, and why could nobody identify the material escaping from it? If it was an asteroid, what force pushed the object hundreds of feet across away from sun than gravity predicted? Solar radiation pressure moves dust grains and thin sheets easily, but usually affects rocks too weakly to explain this observation. Collisions, magnetism, solar wind, and fragmentation were examined, but none immediately reproduced every measured detail without creating fresh difficulties elsewhere. Outgassing remained the favored natural answer, although the absence of visible material prevented that explanation from becoming convincing to everyone. One possibility suggested the object released a gas that telescopes could not detect easily during its brief observable passage Earth. Ordinary comets expel water vapor, carbon dioxide, carbon monoxide, and dust, but alien systems may produce very different chemical proportions. Extremely light molecules could provide significant thrust while carrying little dust, leaving almost no bright coma for astronomers to observe. Molecular hydrogen became especially attractive because it is difficult to detect under these conditions and escapes when warmed by sunlight. The challenge involved creating enough trapped hydrogen and preserving it across an interstellar journey before the object reached our system. An early model imagined Oumuamua as an iceberg containing solid molecular hydrogen, a substance far more volatile than water ice. Solar heating would evaporate that hydrogen, generating acceleration without producing the dust expected from a conventional comet approaching the sun. Erosion during travel might also reshape the body, potentially explaining why brightness measurements suggested an exceptionally elongated or flattened form. However, radiation and faint background heating could destroy hydrogen ice long before any fragment completed a journey between planetary systems. Researchers therefore questioned whether such an iceberg could form naturally, survive for ages, and remain intact until passing beside sun. A later hydrogen model avoided pure hydrogen ice by beginning with a more familiar object made largely from water instead. Cosmic rays traveling through that ice could split water molecules and create molecular hydrogen trapped within microscopic spaces throughout material. When sunlight warmed Oumuamua, the stored hydrogen might escape and generate thrust while releasing almost no detectable dust around body. This approach transformed an exotic iceberg into an ordinary icy planetesimal chemically altered during exposure to interstellar radiation over time. Even this solution remained disputed, because researchers disagreed about whether enough hydrogen could escape rapidly to reproduce the observed acceleration. That disagreement explains why Oumuamua remains unresolved, because each successful model fixes one clue while creating new physical problems elsewhere. Scientists must consider size, shape, rotation, internal strength, heat transfer, composition, acceleration, survival, and abundance together, rather than separately always. A material can produce thrust, but fail to survive, while a durable composition may release too little gas when warmed. A shape can match brightness data, yet require an implausible formation process, or remain too fragile for an interstellar journey. Limited observations allow different assumptions to produce different answers, preventing any single explanation from defeating every serious competing theory completely. The nitrogen ice hypothesis offered perhaps the most dramatic natural story. linking Oumuamua to a world resembling Pluto in composition. Pluto contains broad deposits of frozen nitrogen, and similar dwarf planets may exist around countless stars throughout the galaxy today. Collisions could blast nitrogen-rich fragments from their surfaces, ejecting pieces into interstellar space before gravity could reclaim them again. A flat nitrogen fragment would lose material near the Sun and accelerate through sublimation, without necessarily creating a visible coma. Solar erosion might also reshape that fragment, helping explain the unusual brightness pattern while remaining entirely within known natural physics. If correct, the object was not random debris, but a genuine sample from the surface of an alien dwarf planet. Its chemistry could have revealed geology from a world humanity never see, orbiting a star whose identity has disappeared history. However, critics question whether planetary systems can produce enough nitrogen fragments for our first detection to become statistically reasonable all. Cosmic radiation would also erode nitrogen ice during travel, potentially destroying many fragments before they ever entered another planetary system. The theory matches several clues, but depends upon assumptions regarding exoplutos, collision rates, ejection efficiency, and long-term survival. Another model pictured Oumuamua as an ultra-porous aggregate, more like a giant cosmic snowflake than a solid asteroid body. Such material could possess extremely low density and enormous surface area compared with its mass, allowing sunlight pressure to matter. Planet-forming disks can create fluffy structures from tiny grains, and some could escape before collapsing into denser object stars. Radiation pressure might then produce the measured acceleration without outgassing, because the object would have little mass resisting the force. Yet something so fragile must survive collisions, radiation, tumbling, heating, and a close solar passage, making durability the central objection. Other explanations involved carbon monoxide, carbon dioxide, water ice, or mixed volatiles hidden beneath an insulating crust altered by radiation. Millions of years in space might process only the surface while preserving fresher material within cracks and protected layers below. When the object warmed, gas could escape through narrow vents, providing thrust while carrying little dust for telescopes to notice. This remains attractive because outgassing is common, although observations never identified which volatile substance actually produced the additional acceleration measured. Without a chemical fingerprint, almost any hidden gas becomes possible, but none can be confirmed after target disappeared from view. Fragmentation offered another possibility, suggesting the body may have broken apart before discovery or lost pieces after passing the Sun. Escaping fragments could change its mass and motion without producing a stable coma visible through telescopes during the observing campaign. Structural damage might also explain the tumbling, particularly if a prior collision had left the object fractured and rotating chaotically. However, observers saw no clear swarm of fragments, and the acceleration still followed sunlight too closely for explanation through breakage. Fragmentation may have contributed, but it never provided a complete mechanism capable of satisfying every measurement at the same time. Then came the explanation that captured public imagination, asking whether Oumuamua might represent technology rather than naturally formed planetary debris. The argument began not with signals or machinery, but with solar radiation pressure and the possibility of a thin structure. A light sail can accelerate when photons strike its broad surface, providing propulsion without fuel, engines, visible gas, or exhaust. Advanced civilizations might theoretically send such probes between stars, so several researchers argued that artificial origins deserved examination rather ridicule. Because shape remained uncertain and acceleration remained unusual, the idea could not be dismissed, merely because its implications sounded extraordinary. The artificial proposal became famous because it offered a breathtaking interpretation of humanity's first confirmed visitor from another stellar system. Perhaps the first interstellar object was also the first technology from another civilization encountered inside our solar neighborhood by chance. But possibility is not evidence, and a sail requires low mass, large surface area, and exceptional durability during cosmic travel. No telescope photographed a sail, no controlled navigation appeared, and no artificial light, heat, transmission, or deliberate maneuver was detected. The data allowed speculation, but never required technology, because a force linked with sunlight remained compatible with several natural mechanisms. Breakthrough. Listen used the Green Bank telescope to search Oumuamua across billions of radio channels for evidence of artificial transmission. Under favorable conditions, the observations could have detected an extremely weak transmitter operating near the object during the search period. Nothing appeared, removing the simplest detectable sign of engineering while leaving silent, inactive, damaged, or unfamiliar technologies impossible to exclude. A missing signal did not prove nature, yet it prevented radio evidence from supporting the idea of an intelligent probe. Natural models therefore retained the stronger scientific position, even though no single natural mechanism had completely solved every observational contradiction. The debate became unusually intense because Oumuamua occupied the space between genuine evidence, limited measurements, public imagination, and extraordinary possibility. Science should examine unusual ideas, but it also favors explanations requiring fewer unsupported assumptions when several possibilities match the data. Outgassing has been observed on countless comets, whereas artificial sails from extraterrestrial civilizations have never been confirmed anywhere by instrument. That difference does not make technology impossible, but it demands far stronger evidence before engineering becomes the most reasonable explanation. In this case, the evidence never reached that threshold, so mystery remained justified while certainty about aliens remained unsupported, premature. Another question concerns its birthplace, which astronomers tried tracing backward through the galaxy using the object's incoming direction and speed. The farther calculations extended into the past, the less reliable they became because stars and smaller bodies change their positions. Gravitational encounters alter trajectories, and even tiny uncertainties can grow across hundreds of thousands or millions of years before discovery. Any unmeasured outgassing force would complicate reconstruction further, changing where the object appeared to have traveled before entering our system. Researchers compared possible paths with nearby stars and stellar groups, yet no parent system was identified with convincing confidence afterward. Oumuamua may have wandered for ages, making its original star, planetary environment, and ejection event impossible to reconstruct from motion. It could have formed within an icy disk, on a planet's surface, or inside debris created during a collision elsewhere. A giant planet might have thrown it outward, a star might have disrupted its orbit, or colliding worlds launched fragments. The complete history remained encoded inside the object, but humanity lacked instruments capable of reading that history before it vanished. This lost context makes every composition theory harder to test, because origin and material should constrain other through formation processes. Even without a final explanation, Oumuamua remains scientifically valuable because every planetary system should eject material during formation and evolution. Our giant planets probably scattered numbers of comets and planetesimals into interstellar space during our system's turbulent youth long ago. Some ancient fragments from our neighborhood may now cross distant systems, becoming mysteries for observers around stars humanity cannot identify. Oumuamua proved this exchange occurs, showing that pieces of alien planetary systems can reach us without mission traveling between stars. The galaxy delivers samples, but scientists must discover them early enough to determine what those samples contain before they escape. 2 years later, astronomers discovered 2I Borisov, a second interstellar object that behaved far more like a familiar active comet. It developed a clear coma and tail while approaching the Sun, leaving little doubt about its classification among icy bodies. Spectroscopy revealed gases and dust, allowing scientists to compare material from another planetary system with comets formed around our Sun. Borisov proved that at least some interstellar objects resemble ordinary comets, yet its familiarity made the earlier object seem more unusual by comparison. The first discovery had not defined a standard population, but instead revealed that debris between stars could display remarkable diversity. Because Borisov was active and discovered earlier, astronomers collected chemical information and watched its behavior change as solar heating increased. Gas flowed from its nucleus. Dust surrounded the body, and observations connected visible activity with specific molecules released from surface. Even then, no spacecraft could intercept it, because warning remained short and the hyperbolic trajectory carried the comet away quickly. Humanity had confirmed 2 visitors from other stars, but both departed without direct examination of surfaces, interiors, masses, or structures. The lesson became unmistakable. Telescopes can identify interstellar objects, but only prepared spacecraft can reveal what those objects actually are. In July 2025, astronomers reported 3I Atlas, the third confirmed interstellar visitor, and another clearly active comet entering our neighborhood. This object was detected earlier, allowing observatories and spacecraft across the world to organize a much broader coordinated scientific response. Its strongly hyperbolic orbit confirmed interstellar origin, while visible cometary activity immediately distinguished it from the ambiguous appearance of Oumuamua. Thousands of observations showed no danger to Earth, replacing public speculation with a detailed record of another natural visitor passing. The contrast with 2017 revealed how much science improves when discovery occurs before perihelion rather than after target is escaping. Together, the 3 discoveries transformed interstellar studies from a theoretical subject into an observational field containing different classes of objects. Oumuamua was ambiguous, Borisov was clearly cometary, and 3I Atlas received a far more mature global campaign from discovery onward. Objects ejected from alien systems can form at distances, contain different ices, suffer different collisions, and experience different interstellar histories. Some may resemble comets, others may look asteroidal, while fragments from larger worlds could display properties unlike either familiar group. The next visitor might fit an existing category or force astronomers to invent explanation for materials no object has displayed. The Vera Rubin Observatory should improve these searches by repeatedly surveying wide areas of sky with an enormous digital camera. Its long survey will produce rapid alerts whenever objects brighten, fade, move, or appear where earlier images showed nothing unusual. Rubin should identify huge numbers of asteroids, comets, distant icy bodies, and faint visitors that previous instruments would have missed. Interstellar objects once slipping through unnoticed may become regular discoveries, giving scientists enough examples to compare populations rather than mysteries. Yet detection will remain difficult, especially for dark, inactive bodies that become visible only after approaching the Sun or Earth. Active comets can be detected farther away because gas and dust create bright clouds, while dark objects remain hidden longer. Detection rates will therefore depend not only on abundance, but also on composition, activity, size, color, approach geometry, and timing. Oumuamua suggested small interstellar bodies might be extremely numerous, but one object could never define the complete population by itself. Borisov and 3-Eye Atlas improve statistics, yet 3 visitors remain a tiny sample from a galaxy containing billions of stars. Many objects may currently pass through our system unseen, remaining distant, faint, harmless, and completely beyond the reach of surveys. Some interstellar bodies might become temporarily trapped by planetary gravity, while others could strike planets, moons, the Sun, or Earth. Proving an individual meteor came from another star remains difficult because tiny uncertainties in speed can completely change reconstructed trajectories. Oumuamua itself provided no evidence of life, biological material, living microbes, artificial organisms, or complex chemistry capable of proving panspermia. Its importance was more basic because it demonstrated that solid objects move from planetary system into another across interstellar space. Whether organisms survive ejection, radiation, travel, atmospheric entry, and impact remains a separate question that this visitor never answered science. The most powerful way to solve interstellar mysteries would be visiting object directly before sunlight and distance remove the opportunity. A spacecraft could photograph the surface, map its shape, measure mass, identify gas, analyze dust, and determine structure during flyby. Even the encounter could answer questions that years of arguments cannot settle, replacing assumptions with measurements collected beside target itself. A sample return mission would offer more, but catching a fast hyperbolic body and bringing material home presents extraordinary difficulty. The target remains unknown until discovery, and by then it may already move too rapidly for spacecraft launched from Earth. ESA Comet Interceptor addresses this problem by preparing a spacecraft before scientists know which suitable comet will become its destination. The mission plans to wait near Sun-Earth L2 region, preserving fuel until survey telescopes discover an accessible visitor. Its target is a comet entering the inner solar system for the first time, although an interstellar object could qualify. Multiple components would observe from different directions, creating a picture of the nucleus, surrounding gas, dust, activity, and environmental interaction. Such a mission cannot guarantee interception, because hyperbolic trajectories are fast, unpredictable, and often poorly aligned with any waiting spacecraft. Still, the strategy changes everything by preparing hardware first, then allowing nature to select a target after astronomers discover reachable. Future interceptors might wait at several useful locations, connected with survey networks capable of issuing alerts after hyperbolic discoveries appear. Improved propulsion and rapid mission planning could then convert a fleeting telescope target into a world examined from close range. Researchers have also explored chasing Oumuamua itself through Project Lyra concepts, but its enormous head start creates extreme engineering demands. A pursuing spacecraft might require gravity assists, exceptional speed, and a dangerous close solar passage before spending decades reaching target. Even after catching it, navigation would be difficult because the mission must locate a dark body moving through deep space. Relative speed during encounter could become enormous, leaving only moments for instruments to collect decisive measurements before both objects separate. No approved mission pursues Oumuamua, and most researchers consider direct recovery unlikely without advances in propulsion and long-term funding. Telescopes can no longer see the object, although astronomers can calculate its future path beyond the planets and solar wind. Unless an extraordinary mission succeeds, humanity's first known interstellar visitor will carry its physical evidence back into darkness beyond reach. This is why scientists still cannot fully explain Oumuamua, and why that uncertainty should not be mistaken for scientific failure. We discovered a small, faint, fast object after its closest solar passage when the best opportunities for measurement had vanished. Astronomers gathered enough data to recognize something extraordinary, but not enough information to choose decisively among several physically possible explanations. Science works best when hypotheses face tests. Yet the laboratory in this case disappeared before researchers could design those experiments. The incomplete answer reflects incomplete evidence, not broken physics, hidden knowledge, institutional fear, or proof that scientists ignored in solution. Saying the object remains unresolved does not mean theory deserves equal weight, because evidence supports some mechanisms better than others. Most researchers favor natural explanations involving volatile release, unusual ice, fragmentation, low density, or combinations of several ordinary physical effects. Artificial technology remains possible in principle, but the observations provide no direct evidence requiring intelligence, construction, communication, or controlled navigation. At the same time, nobody can claim the natural mechanism is fully settled, because the material and force remain unidentified. The responsible conclusion stands between sensational certainty and dismissive certainty. Oumuamua was probably natural, but its precise nature remains unknown. The next similar visitor could supply missing evidence if astronomers detect it early enough to observe the approach and departure. Infrared instruments could identify ice, while spectroscopy searches for hydrogen, water, carbon monoxide, carbon dioxide, nitrogen products, and organic molecules. Radar might constrain shape and rotation during a close approach, and thermal measurements could reveal how sunlight changes internal material. A prepared spacecraft could redirect toward the target, converting theoretical debate into direct measurements before distance removes another opportunity again. Instead of reconstructing events after escape, scientists could watch activity begin, evolve, fade, and alter the trajectory throughout the encounter. A second object showing no visible coma and measurable acceleration would transform a unique mystery into a recognizable astronomical class. Matching invisible gas would strengthen comet models, while matching nitrogen signatures would support fragments from exoplanets, resembling Pluto in composition. Consistent radiation pressure behavior might favor porous aggregates, especially if their density, shape, durability, and formation pathways matched theoretical predictions. Science often solves one lost mystery by finding another example under better conditions, rather than recovering the original object itself. Future discoveries could therefore reveal what Oumuamua was, even though the first messenger remains beyond detailed observation and physical sampling. Future visitors may also deepen confusion, because interstellar space collects debris from countless environments shaped by stars and planetary histories. One object might come from a disk, another from an ancient collision, and another from a frozen dwarf planet's surface. Their compositions could vary far beyond comets and asteroids, forcing astronomers to expand categories instead of confirming one universal model. Oumuamua remains haunting because it arrived first, looked asteroidal, moved cometary, tumbled strangely, and accelerated without revealing an obvious tail. Every measurement suggested a possible story, but those stories never aligned, leaving real evidence limited, contradictory, and incomplete for interpretation. The answer is not abandoning questions, but improving surveys, preparing interceptors, building faster spacecraft, and testing competing explanations against visitors. Oumuamua gave no radio message, machinery photograph, or movement requiring intelligence, yet it proved material crosses boundaries between stellar systems. Now telescopes scan wider, computers identify hyperbolic paths faster, observatories share alerts, and missions wait before their targets are known. The messenger arrived and escaped before humanity understood it, leaving information to recognize mystery, but insufficient evidence to solve it. That is why scientists remain confused, not because physics failed, but because Oumuamua disappeared before decisive questions could be answered.